operator with these recurrence equations, let's make it really work for us. So I want to try a more complicated example, and that is, let's find a function f mapping, again, the naturals union 0 to the reals, satisfying, well, we've got now two initial conditions. I want f of 0 to equal 3. I want f of 1 to equal 5. And my recursive part is going to be a lot more complicated. I'm going to want f of n to equal f of n plus 1 minus f of n plus 2 all over 12. So before this, and that might be a little bit hard to read, I'll be using it down here in a second, it'll be pretty clear. That might be a little bit harder to just guess what the answer is. So in the previous examples we had, well, f of n plus 1 was 2 times f of n, like, oh, it doubles every time, or it triples every time, or whatever. So we have just a factor of 2 to the n or a factor of 3 to the n. This might be a little bit harder to deal with just on the surface. So first let's unpack this, and then let's try to write it using the advancement operator. So I'll multiply both sides by 12, and I'm going to get 12 f of n equals f of n plus 1 minus f of n plus 2. Now what I want to do is I want to write this using the advancement operator, and then I'm going to try to put everything involving f on one side and everything else on the other side. In this case, everything involves f, so I'm going to have everything involving f on one side and 0 on the other side. This, just written with the advancement operator, is going to be a f of n, and this is going to be minus a squared f of n. So now I'll put everything on one side, and I'm going to have a squared f of n minus a f of n plus 12 f of n equals 0. Well, this I can factor, and I'm going to get a squared minus a plus 12. Remember the sort of operator theoretic factoring. F of n equals 0. And this is kind of like in the example where we had a minus 3 times f of n. That wasn't just straight up multiplication, but sort of a minus 3 operating on f of n. So again, I'm going to avoid too many details. But now this I can factor, and this becomes a minus 4 times a plus 3 operating on f of n. And again, this is not standard multiplication. This is sort of an operator theoretical way to write this. So using the analogy of multiplication, though, if I've got this times this equals 0, that means either I have a minus 4 f of n is equal to 0, or a plus 3 f of n is equal to 0. Because again, I'm viewing these as, sort of, this is an operator applied to a function. This is an operator applied to a function. Well, if I had a minus 4 applied to f of n was equal to 0, this is going to look a lot like this looks a lot like that previous example. This means that my answer is going to look like, well, f of n equals c1 times 4 to the n. Or I've got, if this was the solution, this is the root here would be negative 3. This would mean that f of n was equal to, let's call it c2, some other constant, negative 3 to the n. Now these are, either one of these could be a solution, but putatively. But what I want to do is I want to keep track of them separately. So I'm going to call this f1 of n and f2 of n. These are sort of separate parts of the function, and my answer is going to be of the form f of n equals f1 of n plus f2 of n. Now, if you've been through a course in differential equations, this should look familiar. If you haven't, it might be a little weird. I've waved my hands through this operator theory. Sometimes I'm saying it's multiplication when it suits me. Sometimes I'm saying it's not when it suits me. And maybe you've forgiven me for that. But now here I'm just telling you I need two different parts of this function. If you're still not 100% convinced, I would say, which that's perfectly fair, I would say let's just go a little bit further, and hopefully in hindsight you'll see why these moves work. So a lot of this is a formal manipulation, and I'm not giving you rigorous proofs of every single step. But let's just suppose that our function is of this shape or this general form, and now let's proceed as before and plug in our initial conditions. So I'm going to set 3 equal to f of 0, which is f1 of 0, so this is c1 4 to the 0, plus f2 of 0, c2 negative 3 to the 0. So these things go away. The c1's still here. And I get c1 plus c2. Now I plug in my second initial condition, and I have 5 equals f of 1, which is c1 4 to the first power plus c2 negative 3 to the first power. And this is going to give me, well, 4c1 minus 3c2. So what do I have here? If I collect this information, we can see that I've got a system of two equations with two unknowns. c1 plus c2 equals 3. 4c1 minus 3c2 equals 5. And if I can solve this system of two equations and two unknowns, what am I going to get? Well, I'm going to get that c1 equals 2 and c2 equals 1. So you can, choose your favorite method of linear algebra to get here, but you can just check that it works. 2 plus 1 is 3, 8 minus 3 is 5, which tells me that my final answer is going to be f of n equals, well, c1 2 times 4 to the n plus 1 times negative 3 to the n. And that's my final answer. And hopefully, even if it wasn't 100% clear, hopefully you can see that this advancement operator at least allowed us to organize our information a little bit differently, so we didn't get bogged down in maybe some of the things that could have tripped us up. We're hopefully a little bit more comfortable with the advancement operator and how it works with recurrence equations. We can do some more complicated stuff. So I want to give you now an example of an advancement operator approach to a recurrence equation that's going to have sort of repeated roots in the advancement operator polynomial. So to see how this works, we're going to look for a function mapping, again, the naturals union 0 to the reals, and satisfying, again, two initial conditions, f of 0 equals 2, f of 1 equals 9, and this recurrence, which is f of n equals 3 f of n plus 1 minus f of n plus 2. And I'm going to divide all that by 9. Now I'm going to approach this just the same way as I did the previous one. So I'll start by rewriting this using the advancement operator. And to rewrite this using the advancement operator, I'm going to get 9f of n equals 3 f of n plus 1 minus f of n plus 2. This is, of course, the same as saying 9f of n equals 3a f of n minus a squared f of n. Now when I put all this together, I get a squared, and I'm also going to factor, minus 3a plus 9 times f of n equals 0. But you notice this is a repeated root, right? This gives me a minus 3 quantity squared f of n. That is, I'm applying this operator to my function twice. Well, if I were to just run down and attempt to say, okay, a minus 3 f of n, so this is not going to work, so so let's just pretend that we say, well, let's let f of n equal some constant times 3 to the n, and then we plug in our initial data. Well, let's do this. 2 equals f of 0 equals c times 3 to the 0, which tells me c equals 2. 9 equals f of 1 equals c times 3 to the 1, which tells me that c equals 3. And that's a problem because 2 does not equal 3. So if I try to just, go straight for the jugular without carefully dealing with this repeated root situation, I'm going to end up with some abject failure. So that is to say that just treating this like a minus 3 is not going to work. So this was my poor attempt. Now let's do something that will actually work. This 3 is bugging me. It's got a little extra knob on it I didn't like. So if you've seen differential equations, you probably have some guess as to how we're going to proceed. If we have something like this happen in the case of differential equations, we get 2 components, one of them with an extra copy of the variable. So that's what we're going to do here. We're going to say, well, let's let f1 of n equal 3 to the n times c1, and let's let f2 of n be, again, 3 to the n, but now times n times some other constant, c2. So with this, I'm getting sort of both factors of that advancement operator captured in my data here. If this kind of jumps out of nowhere, I'm sorry, this is just something that happens to work, and my perception is that a lot of the study of differential equations and such things tends to be, well, this is what we've found that works. So if you have a repeated root here, I want you to try throwing in a factor of n. Now, with this, it's just a trick that it makes sense, but if you haven't seen it before, it might be a little confusing. But let's just try. Let's see what happens. So again, I want f to be the sum of f1 and f2, and let's plug in my initial data. So 2 equals f of 0, which is going to be c1 times 3 to the 0 plus c2 times 0, don't forget this n here, times 3 to the 0. So this just tells me that c1 equals 2. Now my next initial condition is that 9 equals f of 1, so that's c1 times 3 to the first power plus c2 times 1 times 3 to the first power. And because I know what c1 is, I can just plug that in. So I get 9 equals, this is, I'm applying this now, 2 times 3, 6 plus 3c1, which tells me that c1 is equal to 1. So my final answer is going to be f of n equals, well, c1 is 2 times 3 to the n plus n times 1 times 3 to the n. And that's how I'm going to deal with repeated roots.